connecting the world and the universe. My name is Professor Martin Thuo, coming to you from the Eastern United States at North Carolina State University. This month, we have had the privilege of hosting Joshua Bogard and a team of very excellent women during our Women's Day. And today we are privileged to have Yanlin Song from the Institute of Chemistry, Chinese Academy of Science. Also join us next week when we dive into the world of cognition and molecular electronics with Professor Wilfred Viel. Today I'll be assisted by a panel here consisting of Hong Bon Sun, Nick Fang, Alice, and Shitov Shen is going to be our challenger. Our speaker today is Professor Yanlin Song from the Institute of Chemistry, Chinese Academy of Science. Professor Song is an established scientist. He is the director of the Key Laboratory of Green Printing at the Institute of Chemistry, the Chinese Academy of Science. He's done a very interdisciplinary work that has resulted to over 500 publications and has an H index of 100. He's been granted over 170 patents and has won many, many awards. I'm not going to go through all of them. Otherwise, I'm going to be giving the talk. He has received the National Distinguished Young Scientist Fund in 2006, the Changjiang Scholar Distinguished Professor in 2016, the National Natural Science Second Prize in 2005 and 2008, and the National Innovation Competition in 2023. And today he's going to be talking to us about nano green printing and manufacturing technology. Professor Song.
Thank you, Martin. I would like also thank Alice for inviting me to give this talk. And also Professor Xun and Professor Fang for your time. Today, I would like to talk about a story about printing. My topic is nano-green printing and manufacturing technology. I am from Institute of Chemistry, Chinese Academy of Science, Beijing. What do we do? 4 years ago, CCTV have a special program named The Power of Science for celebration of 70th anniversary of PR China.
这不是电脑动画，是高速摄像机拍下的真实场景。通过纳米技术，科学家可以随心所欲地控制液滴的形态。
普通的水滴落在固体表面，一种是弹跳，一种是溅射开。但是这样一个非常奇特的现象，它可以旋转起来，这个是以前从来没有发现过的。
This is the power of science. Actually, in my group, we focus on the fabrication and application of new printing materials and technology. We use different nanomaterials as ink and print on different surfaces to form different patterned functional materials, and use these materials for application in different fields. We have published more than 600 papers with a H index of 109, and we have published 16 books in different countries and granted more than 170 patents in different countries, and with more than 50 cover papers. And Nature have highlighted our research 4 years ago with the topic, the Chinese researcher painting the printing industry green. So what means green? It means we use a more additive manufacture process to replace the traditional high pollution etching process. And science have also highlighted our work on control the dynamic behavior of an ink droplet. In fact, in the history of printing technology, we have a concave, convex plate. We have also multiple type of plate. It's very famous in China. And we have also laser phototype setting plate. It occurred about 40 years ago. Developed by Professor Xuan Wang at Peking University. It influenced the China printing industry greatly. The process for laser phototype setting technology is just like the traditional way we make a photo. It needs 2 steps. Firstly, the computer can transform the signal with a laser to a photosensitive film, and the film will be developed in dark room and used as a mask. This mask covers the photosensitive plate, and during the second operation in dark room, we can achieve a printing plate. And it's just the same way we make a photo 30 years ago. And it need a chemical developing process and need to remove the unprinting area, and it etching process. So it is usually expensive, complex, and should be operated in dark room with heavy pollution. About 15 years ago, we developed a new process to print with nanomaterials based on our knowledge on control the surface of the energy of materials. We printed an aphilic pattern on a hydrophilic surface. So the pattern can absorb ink, and the blank is hydrophilic, it can't absorb ink. So we can print newspapers and books directly without any etching process and needn't operate in dark room. So the key is the pattern is aphilic and the blank is hydrophilic. It based on our knowledge on chemistry and the surface property of different materials. It's just like a digital camera replaces the film one. It totally avoids the complex process and the heavy pollution of the traditional way. It can avoid millions of tons of water solution and can saving hundreds tons silver and tons of aluminum. From the principle, it is reducing the photosensitive coating solvent. And it has been applied in China in the printing factory and for printing newspapers and books. We have won the most famous Bison printing prize. In 2018, CCTV have also a special program to introduce the printing achievement in China. They introduce the concave convex plate, the multiple type of plate, also the laser typesetting plate. They invited Professor Chen, the wife of Professor Xuan Wang, introduced their their technology for printing. And our group will also be invited to introduce our new printing technologies based on nanomaterials. I also report our research to Professor Chen and send a gift to Professor Chen. This is the picture is made of special materials. Yeah, we want to replace pigment or dye to show color. Usually, we can see different color. We must use different dyes, but the process to produce dye is heavy pollution. So 20 years ago, we note that in nature there are many beautiful color, such as the wing of a butterfly and this opal in Australia. And this beautiful color, not because of dye or pigment. It is arranged from the very ordered microstructure, a nanoscale, and when the period of the structure overlaps the wavelength of visible light, it will appear different color. But the physical mechanism is it is a special photon semiconductor, also called photonic crystal. It's also a metamaterials. So this is a very interesting material. Our group focus on the physical fabrication and the new application of these materials. So during the past 20 years, we synthesize this very ordered, very monodispersed nanoparticle, basic chemical method, and with a different diameter, will appear different color. It means a different photonic bond gap. Compared to the traditional method, our synthesis method can avoid the complex precision producer, and we greatly improve the mechanical strength because the nanoparticle reported before is usually based on polystyrene or silicon oxide, but we designed a special co-cell structure nanoparticle. With the hard core, we can keep the size of the particle. With a soft cell, and we have many hydrogen bond among the surface. So the interaction of the particle can be enhanced greatly, and we control the size of the particle. We can achieve different color, and then furthermore, we can improve the mechanical strength based on the strong hydrogen bond among the surface. So far, we can produce this nanoparticle in large scale, and we can use it as for spray coating on different substrates, such as paper, plastic film, and metallic plate. We can also use this solution as ink to print by inkjet printing directly to form a desired pattern. Yeah, you see this flower and the leaf are made of different nanoparticle with a different size, but the chemical structure is the same. So far, we have achieved a large-scale production and use for different for coating and other applications. You can see from different angle, you can see different color. This butterfly, it's very fancy. We can also apply these materials for some famous products. Yeah. However, I can't use their labels. Yeah. Yeah, because it's metamaterials as photonic crystal can be used for enhancing the fluorescence signal. Yeah, so it can be used for ultra trace detection. You can see this beetle. It can live in desert because it has a special back. The back usually are hydrophobic, but it has hydrophilic pattern. So the hydrophilic domain can absorb ink, absorb water in the environment. And based on this principle, we can print hydrophilic pattern on a hydrophobic surface. Just like the video I showed at the beginning, when a droplet hit this surface, it will be split to different parts. And based on this different part, we can detect many different signals. And the signal also be enhanced by photonic crystal. Yeah, when the band gap corresponding the wavelength of the fluorescence. And based on this, we can print label-free protein detection chips. We print hydrophilic detect area on a hydrophobic surface. And based on this printed chip, we can achieve high performance material ENS recognition. Yeah, you know, for a complex solution, it is hard for separation. So with this printed soft chips, we needn't separate different ENS from the solution. We can directly detect as many as 12 different metal ENS use one chip. We also can print on plastics for this flexible detect chips for multisaccharide recognition. You know, saccharides have very similar chemical structures, so it is hard to separate a complex of saccharides. So with this printed flexible chips, we can detect 12 saccharides without a separation. Three years ago, we suffered from COVID-19. So based on this printed photonic chips, we can also achieve the detection of COVID-19 reversible. And within 10 minutes, we can even biomorphing to detect the COVID-19. Yeah, we also developed very simple machine, and if the machine show a green signal, it means negative. If the machine show a red signal, it means positive. So very simple and very rapid. So above research based on our printing technology use nanoparticle as ink and to assemble this nanoparticle to achieve photonic crystal structure. Based on this photonic crystal structure, it can enhance the fluorescence signal, and we have applied it in the high sensitive detection. If we use conductive nanoparticle such as silver or copper nanoparticle and golden nanoparticle, and we can achieve conductive circuits because everyone have a electrical device. We need to have circles, and traditionally the circles also produced based on etching process. Firstly, we should make a mask. It's based on photosensitive materials on a film, and we operate in darkroom to achieve this mask. And secondly, use this mask as a template to cover plastics covered with copper. And based on an etching process, we can achieve the patented copper pattern. And most of the copper are wasted, and this process is heavy pollution. So it is very similar with the traditional way we make a plate. So it also carried printed PCB, printed circles. So our idea is use an additive method to avoid the etching process. We can use silver, golden, and copper nanoparticle as ink, and use this ink, we can print directly the conductor line. And yearly, we have achieved a large-scale production of silver nanoparticle and nanowires. We have also transferred this technology from laboratory to industry with high scalable production of conductor ink, and we have printed different electrical cards, such as the subway railway tickets over Beijing, Hong Kong, and also we have printed the APEC meeting tickets just 10 years ago in Beijing. Yeah, if we can print the circles, we can apply the printing technology in many fields, such as lighting and the wearable or flexible device, many applications. But what is the fundamental challenge? So far, we just talk about the green process, use the additive process replace the traditional etching process. How about the nanoscale? About 10 years ago, people usually think it is impossible by printing technology to achieve nanoscale pattern. Yeah, because it had 3 fundamental challenges. It related to the weighting, coercion, and the assembly behavior of droplets. For example, if we want to achieve a nanoscale dot, we will meet a famous effect named as coffee ring effect. A droplet of coffee on a surface during the evaporation process, the droplet of coffee will spread, and it usually we can only achieve a micrometer scale dot. So how to achieve nanoscale dot is a challenge. So we with a different idea. We control the surface energy of the materials, and we investigate the relationship between the ink droplet and the surface. We can control the three-phase line moved during the evaporation process. It not like the traditional way spread, it but shrink. So with the evaporation, the dot will shrink greatly, and the dot becomes small and small. So at last, we can even achieve just a dot, just 1 particle, 2 particle, 3, 4, 5, 6. We can exactly control the number of particles in 1 droplet. So we can achieve, at last, we can achieve nanoscale dot. So we call it the smallest dot in the world. And the second challenge is how to achieve nanoscale line. It also related challenge named relay instability. This topic is investigated, have been discussed more than 100 years. And based on our knowledge on relay instability, we can avoid the traditional way. Yeah, traditional way, when two droplets meet together, usually we can only achieve this zigzag line. We can hardly achieve this straight line in macro scale. So if we know more about the relay instability, at last we can achieve this single particle line, double particle line, not only straight line, but also curves. So the third challenge is how to achieve the uniform film with a single particle thickness. So it also relates a famous problem named the Marconi effect. It means during the evaporation process, the capillary force and the evaporation speed and the movement of the substance in the ink is a complex question. So we have spent more than 5 years in this question. And at last, we can achieve this thin film at a single nanoparticle scale, and even achieve large scale single crystal. Furthermore, we want to achieve very, very fine three-dimensional macrostructure. Traditionally, people think when the droplet of ink out of the printer, it out of control. So, but we study the behavior of a droplet hit on a surface, how to control the three-dimensional macrostructure during its evaporation process. So in other group, they usually hardly can achieve the same three-dimensional macrostructure by printing technology. But we can achieve exactly the macrostructure, the size, the morphology, and even the direction. So it makes it possible to achieve printing in one droplet, 3D printing in one droplet. And we change the materials. We can print the tooth, use one droplet. It totally avoids the etching process and without any Western materials, totally transfer the target product. We can also use hydrogel to print the contact lens. They have very certified property, and it can be used for this contact lens at a very cheap price, very rapid process, and it can be designed according to the person who need it. We also use our technology because we can exactly control each droplet to design the three-dimensional morphology. So we use one droplet as a dot of a border. You know, traditionally, it use we should have a special paper and use a pin like a needle to make this broadening words. And based on our technology, we can use common paper, commercial paper, and print the not only words but also image or pictures. So the blind children can also play toys such as this magical products and This technology has been applied in China and other countries, and in subway railway, in airport, and we have made the first map for blind people in Fujian province, and the guidance for blind people in Shanghai subway railway, and also Nanjing Museum. During the Olympic Winter Games in Beijing 2 years ago, and the last year Asian Games Hangzhou, we have also applied our printing technology for blind people, and this greatly helps them to know the information during the games process. This technology has been also applied in other countries. And if we can exactly control the three-dimensional microstructure, we have a more challenging idea. You know, more than 300 years ago, Isaac Newton invented triple prism. Yeah, based on triple prism, we know the sunlight are made of 7 colors. So I have an idea that if we printed each droplet into a triple prism, we can see our desired color from the same ink. And based on this idea, my students investigate the possibility to print the full color image, use one kind ink, just based on the different microstructure. At last, we printed the desired spherical crane structure. So different microstructure will appear different color. So based on this technology, we can achieve very fine colors image just with use transparent ink. So this is totally different from our textbook. It draws great attention all over the world. So Professor have Larry Zigzag at the UPenn said that I was excited to see that somebody had used the strategic color for this process. It is even a philosophy concept. We can use uncolor to no color, colorless to color. We have more interesting finding during our research. You know, Isaac Newton have many contributions to science, and we know the famous Newton's law of impact. Many people have done this experiment during high school, and the collision only alerts the speed and the direction of the object's movement, not the moving type. Yeah, this is our knowledge before about the hitting. But for droplet, for ink, when the ink hit a patterned surface, it has a different phenomenon. You can see these droplets can spin, not only spread. How to spin? Why to spin? We have investigated in detail, and we found the size of the droplet, the symmetry of the pattern include the rotational symmetry and the mirror symmetry. So these 3 conditions decide the dynamic behavior of the droplet. So it's funny and interesting. It means we can make the use of the energy of a rain droplet for electric use. We have confirmed it. Times New York have a special program to introduce our finding.
I bet you've never seen water do this. Twist and turn like a dancer in flight. It happens when a droplet lands on a water-repellent surface with a special pattern. These acrobatic leaps were recorded by Chinese scientists investigating new ways to manipulate water. To understand what they did, let's step back and see what Isaac Newton had to say about bouncing objects. According to Newton, when an object hits a solid surface, some of the energy of the impact is translated into a rebound. Think of a ball hitting concrete. If the ball travels straight down with no spin, it should bounce straight up again. And it's the same with a water droplet on a water-repellent surface. Theoretically, the droplet should bounce straight up, no fancy stuff. But the researchers created a pattern of adhesive material on the surface that water sticks to. The water in contact with the sticky patches recoils more slowly than the water touching the repellent surface, and that makes the droplet spin. Change the pattern of the adhesive, and you change the shape of the dancing droplet. The researchers made swirls and half moons and dotted circles, each of which caused the water to behave differently, sometimes even bouncing sideways. Scientists also showed how the energy of the droplets could be harvested. They set up a magnetically suspended surface. As the droplet landed on the surface and rebounded, it pushed down the plate and caused it to spin. It's a new kind of hydropower. And at their peak, those droplets are spinning at a whopping 7,300 revolutions per minute. So apart from creating a water droplet ballet, scientists have also found a new way to harvest energy. And their work might help in designing self-cleaning airplane wings. For now, it's enough to have the pleasure of watching the leaps and pirouettes of those dancing drops.
NHK TV in Japan also reports this fancy phenomenon to the children of Japan, because this finding is different from their knowledge in textbook. We can also patent not only droplet but also bubbles. So, on a hot pot, you can see a film of bubbles. If we print pattern on the surface of a pot, the bubble will drive the droplet move, and we can design the pattern and to drive the droplet move quickly. It also based on the adhesive of the droplet on the patterned surface. And one droplet water can make work for more than 1 minute. It's a new energy generator. We can also use this phenomenon for chemical reaction.
Sure.
And we can control the movement of a droplet, split, transport, rotation, and release. So it's a basic behavior of a chemical reaction. So we can achieve the single droplet reaction, chemical reaction, based on we control the behavior of a domestic behavioral droplet. We can also control the behavior of a droplet for stepwise chemical reaction and also to deliver drugs to desired position. So this shows a great potential of printing, control the behavior of droplets. So based on this knowledge, we can use different materials as ink, and we can even printing everything. For example, we can print high transparent touch panel without etching process, because the traditional way make a touch panel is based on etching process of ITO glass. It is a complex, high expensive, and with heavy pollution. So with the additive printing technology, we can directly print high transparent, high conductive touch panel. And we can also use quantum dots as ink. We can print quantum dot based high performance display device. We can also print a wearable solar cell based on perovskite materials. We use perovskite as ink. We can print easily the wearable solar cell. So far, we have you can use a special printed soft structure, and we can use this flexible device for charging our mobile phone. So the challenge is still how to achieve nanoscale pattern. So we know covariance effect, we know relay instability, we know Marconi effect. We can control precisely the printed microstructure from 0-dimensional to 3-dimensional. But how to achieve nanoscale pattern? So 10 years ago, we used a template silicon pillars as a template. We use a very thin solution as ink, so we can exactly control the dynamic behavior of a droplet during its evaporation process. So we can control, just like a droplet of coffee. When finally we can control the coffee into a lane, a one-dimensional lane, and the scale is about 30 nanometers on silicon wafer. So it may be a possible approach achieve chips without a high resolution lithography machine. We can not only achieve straight line, but also achieve this zigzag, desired zigzag, different zigzag line with the resolution of a single nanoparticle. And we can also use two kinds of material, different nanoparticles. The green particle is much larger. The red one is smaller. So with this complex as ink, at last, after the printed process, the larger one assembled together and the smaller one assembled together. This straight line, the curves, and the different period of the course can be achieved. It means we can print our desired from 0-dimensional to 3-dimensional, from microscale to nanoscale. So it may be rarely possible to achieve nanoscale device. But another challenge is how to connect different devices on a chip. Traditionally, it seems a problem for mathematics that desired different pattern and to achieve the best way to connect them. We are chemists. We have not much mathematical knowledge. We can learn from nature. We learn ants and bees. During the process to finding their food, they must run the best way. What is the best way? I gave a concept, the lowest energy consumption. So use this principle for printing. We can pin the ink on the desired part and between them, the droplet can evaporation. So at last, it have the desired natural connect. And during this natural connect, it can avoid about a 2/3 decrease in the electromagnetic interface. Because the traditional way, usually the designed parallel lens, the two parallel lens have strong electromagnetic interface. Our method have many this 120 angle connect. It avoids the EMI. Yeah. Another challenge is how to achieve 3-dimensional nanoscale structure. It is impossible for a traditional way to achieve this nanoscale complex 3-dimensional pattern. Even this line at the scale of 10 nanometer. So based on our knowledge, exactly control the evaporation process of a droplet, we can achieve from 1-dimensional to 3-dimensional, from general 3-dimensional to this complex and this line. And use this method, we can print, use 2 different quantum dots as ink. We can achieve this very fine 3-dimensional device. And what is the limitation? Can we achieve molecular scale pattern by printing technology? About 10 years ago, we think about, could we pattern the bubble? You know, the bubble, the well of a bubble is made of surface strain. Surface strain, if the bubble can be patterned, when the bubble disappeared, it will result surface strain line. We also use the template, the pillar, we control the pillar interval, and we can trap bubble. It's very challenging because we know a famous scientist named Oswald Friedrich Wilhelm. Yeah, he won the chemical Nobel Prize in 1909. He has a concept named Oswald repinning. It means when a bigger droplet, a bigger bubble meet a smaller one, the bigger one will consume the smaller one. It's the jingle law in sense. If we want to pattern the bubble, we must avoid anti-Oswald repinning. So we design a special template. We can pin bubble among the pillar template. We can control the temperature and the pressure of the bubble. Finally, we can achieve our desired pattern. If the bubble disappeared, we can achieve the result molecular scale pattern. We use this method to print different nanoparticle pattern and also molecular pattern. With functional molecular, we can achieve molecular scale. Yeah, the electro and optical device. What is special? If we change the morphology of one bubble, the neighbor bubble will change. So just like we know, there is no the same wing of a dragonfly in the world. We can achieve a contactile gas by printing method. This is topological pattern. This topological pattern, this is random pattern, a random jet jets can avoid this familiar phenomenon. If we make a photo, use our mobile phone from a screen, we will find this more fringe because the two devices have an interface. So use this topological touch panel, we can totally avoid this. So it has a greater potential for high performance display in the future. We can also use printing technology to help paralytic people. A few years ago, we have a famous challenge action named Ice Bucket Challenge. Many famous persons poured ice water on their head. They want to help a kind of people named paralytic people. These people can't speak, even can't move, but are alive. The eyeball of these people can move. The movement of the eyeball will corresponding to different thought and different emotion. So if we pass the high sensitive printed sensor around the eye of the people, our our mobile phone will receive the different mask, and we can know this if this person is happy or unhappy. So this printed sensor can can help these people can't speed totally. We can also print this flexible device to help supporter, to help them to design and improve their behavior on in games. And based on this research, we have spent about 20 years in this field. We are still managed to transfer our innovation in laboratory to industry. We have set up an industrial park and set up new companies. And we have also collaborated experts from different countries. We discuss the technology, and we discuss the standard for the new technology. We were also in charge of a new standard for printing a device 4 years ago. And as a summary, during the past 20 years, we have focused on the printing technology. Firstly, we avoid the traditional heavy pollution during plate making process. We named it as green printing, with additive process replace the etching process. The resolution is 10th micrometer. After 5 years, we extend the printing technology to printed electronics. The resolution we can achieve a few micrometer. About 5 years later, we printed a photonic crystal and applied it in medical, in high sensitivity detection device. The typical resolution is 100 nanometers. 5 years ago, 10 years ago, we achieved nanoscale printing. The resolution is about 10 nanometers. So far in my group, in our laboratory, we focus on the molecular printing, even single molecular scale resolution. We should overcome the Marconi effect, covering effect, and we use bubble template for printing. So my story is end. So the keyword is we use an additive process without waste and pollution. We can achieve ultra high resolution, and it's a new universal approach for different materials and different fields. So thank you very much for your attention. Yeah, actually, in my group on the web, I have a special words for our dreams. We want to print from impossible to impossible. The world is very similar, but we can invent it. Thank you very much. Thank you.
Thank you very much, Professor Song.
Yeah.
I like your quote from impossible to impossible, and the fact that you're saying I can. We believe that you can too. So thank you for an excellent talk. We truly appreciate. And now we're going to move to our panel discussion, and I want to first introduce our panelists. Our challenger today is Shitao Shen. He is a postdoc at the Integrated Circuit School of Peking University, where he's working with Professor Wei Wan. He obtained his PhD in microelectronics and solid-state electronics from South China Normal University, where he worked with Professor Yanlin Shui. His research is focused on microfluidic particle assembly and manipulation, and has been published in very high impact journals. Particle assembly and has been. Okay, our next panelist is Hongbo Sun. He received his BS and PhD from Yanlin University in China. He worked as a postdoc in the Satellite Venture Business Laboratory at University of Tokushima in Japan, and then started his independent career as an assistant professor in the Department of Applied Physics at Osaka University. But then in 2004, he was promoted to full professor and was a Zhangjiang Scholar in Yanlin University. And then from 2017, has been working at Tsinghua University. His research focuses on ultra-fast optoelectronics, particularly on laser nanofabrication and ultra-fast spectroscopy. He's published about 500 papers, which are very well cited. He's currently the editor-in-chief of Light Science and Application and deputy editor-in-chief of Photonics. Both are Nature journals. He's a fellow of IEEE, OSA, and SPIE. Our next panelist is not new to iCANX community, but we welcome you back, Nick. Nick Fang received his BS and MS in physics from Nanjing University, and then moved to the US and got a PhD in mechanical engineering from UCLA. He's currently a professor of mechanical engineering at MIT, but prior to MIT, he was in the Midwest, where he was at University of Illinois, Urbana-Champaign. Nick's area of research is in nanophotonics and nanofabrication, and he's very well recognized and awarded for this work. And this includes the ASME Chow and Trigger Manufacturing Engineering Award, the ICO Prize for International Commission from the International Commission of Optics, and was awarded the Career Award, very prestigious here in the US, in 2009, and was named in MIT Technology Review magazine's 35 Young Innovators in 2008. Welcome, everybody. Oh, sorry, we have Alice. Alice is not new to everyone. She's the reason we're here. She's the founder of iCANX and has been driving us to share science across the world. So thank you very much, Alice, for this platform. And with that, I welcome everyone. And we want to start questions with our challenger, Shitao.
Yeah, I'm here. Thank you for introducing. Thanks for your impressive talk, Professor Song. Your work is really cool and fantastic. The manipulation of droplet shape is indeed challenging. You should ask the mechanism, methods, and good applications of controlling liquid interface, shaping the droplet, and building assembly structures from different materials, especially printing droplet onto paper to help blind people to read. It's very significant and a valuable application in the real world. My first question is about the phenomenon of droplet dancing is quite interesting. I'm curious about how the droplets are fixed, can be fixed onto the paper when printing books for blind people to read. Are there some particles within droplet? I guess, I'm not sure.
Yeah, thank you. The droplet can absorb on a hydrophilic area, and the hydrophobic surface will twist the droplet. So we can design different symmetry pattern, hydrophilic pattern. and the hydrophilic part will absorb the droplet. And when the droplet hit the surface, it has will be twist. So the twist behavior will change the moment from a spread to spring. So it based on our design, the pattern of the surface with the asymmetry hydrophilic pattern. The asymmetry will offer a twist source.
Thank you very much. My next question is about one-dimensional assembly structures in your work. I found your work on one-dimensional assembly structures can be used as a biosensor in such as detecting for COVID-19. Could you elaborate on the specific advantages of one-dimensional structures compared to two-dimensional photonics crystals or three-dimensional when they are used as a biosensor?
Yeah, for the very fine one-dimensional structure based on assembly of nanoparticles, the structure has a special scattering phenomenon. The scattering has different corresponding colors. So when the one-dimensional particle length absorb a converter 19 particle, the color of the one-dimensional the pattern, we name it as a chip, will change. So very fine the color change can be detected. So we also use the antibody cover the one-dimensional structure. So the antibody will recognize whether it is converter 19 or not. So it is the mechanism. Thank you.
Thank you very much. Thank you.
Welcome.
Thank you. Yeah.
All right.
Yeah.
Thank you. Any other panelists?
Hello. Yeah. Okay, Nick. Yeah. You are experts. Yeah. Give me a chance, to ask the first. Maybe this was a stupid question or something. Yeah. Professor Song, I think you are magic. You play magic. So, can you still print it the oil like the particles like other like this kind of things for the same patterns or something? Yeah.
Yes. Yeah, we can use different materials. Use this material, we can transfer it into hydrophilic or hydrophobic ink, and the different property of the ink will correspond different substrates. Here, actually, we focus on the interaction of the droplet with the surface, so we can control the morphology of the ink droplet during its evaporation process from 0-dimensional to 3-dimensional, and also focus on the dynamic behavior of the droplet. So it's different from other group of research. Thank you.
Okay, great. Okay, Nick, please go ahead.
Thank you, Yanlin. I really appreciate your wonderful talk. Always inspiring when I listen all of the different research progress you made. So one thing that caught my eye was your notion of molecular printing, right? So I envision that in order to print using the approach that you described, you may have to rely on, so to speak, a assembly and formation of contact line, right?
Yeah.
So I'm wondering, how precisely, we can control contact line in that way. If we want to accomplish, for example, nanometer or even sub-nanometer, so to speak, precision and accuracy in your case.
Yeah, good question. Yes, this is a key point. Yeah, actually, so we investigated the behavior of ink droplet based on the TCL, three phase length, the kinetic length and the capillary is a key point. But for different materials, it is difficult to make different materials to desired dynamic behavior on a desired surface. So this is the key point. So to achieve molecular pattern, we have tried many methods, but at last we can only succeed in bubble as template. Yeah, because the wall of a bubble is made of sufficient, and but the key is how to make the bubble to desired pattern. So we use a pillar, silicon pillar as template. Use this silicon pillar to control the temperature of the bubble and the pressure in the bubble. So at last, with the balanced pressure, every bubble achieve the same structure. Yeah, when the bubble disappeared, the wall of the bubble can achieve molecular assembly. So this is how dear. The key also control the contact length, the liquid, gas, and the solid the contact length is a key point. Thank you.
Go ahead.
Yes, thank you.
I think in average, I have chance perhaps once a year to hear you your talk, and I'm always astonished to see your research progress, and very good. So I may ask you two questions that sounds somehow mean and kind to you, since Haixia encouraged us to ask this kind of question. I think the first is, I think you are really a master of the surface and interface force manipulation. I think the nature of for this kind of force is the van der Waals force. So this yeah. I think, do you have any group or some young researcher to do the quantitative calculation for the material design? I think this is very important since you already pushed the direction to the industrial. I think the cost-effective material and stable material is definitely necessary. So what is your efforts towards such direction?
Yeah, thank you for your suggestion. Yeah, actually, we are chemists. We know how to make it, but the fundamental mechanism is still not so clear. Yeah, because such as the point is quantum phenomenon and other related principle. So maybe we can discuss further. Yeah. And you are physical background, so we have collaborated 10 years ago. So I look forward to collaborating with you on our interested topic in the future.
Also, another question is, for printing, and it is somehow a sunset direction, the sunset industry. Certainly for the electronic device printing, it's very good, and for the braille printing also sounds very reasonable. But for newspaper and books, we already have the laser printing, this kind of technology, which is not very expensive and already very widely accepted. So how do you think about the nano green printing? Is it reasonable to use for print newspaper and books? Because in this case, the cost is very sensitive. what do you think is the future of your technology?
Yeah, the advantage of our printing technology compared to the traditional laser typesetting plate is it's a totally green process. It means it totally avoids the traditional two-step induction, the etching process. Each step need to have many pollution, chemical solutions to outside. And our process is totally an additive process with it hardly have any wasted materials. So my concept is without wasted materials, without pollution. So the most important advantage is it's a clean process, and it also cheap because it avoids use many expensive materials such as silver-based photosensitive materials. So it also, unfortunately, is people hardly read the newspapers, books. Usually we use mobile phone. So we have to transfer our research from printing newspaper and books to other use other materials as ink to for other field application. So about 10 years ago, we transfer our interest from traditional printing for newspapers and books to electronics. And based on this, we also use special materials for photonic crystal as ink. We so far we have applied a new research field. We named as printed photonics, and also we want to break through the limitation in resolution for printing. Yeah, about 10 years ago, yeah, the expert in printing industry, almost all of them think printing technology can only achieve macro scale resolution. So they double to our concept, not green printing. Yeah, because 10 years ago, we only use nanomaterials as ink. We can't achieve nanoscale resolution. So we have to achieve nanoscale pattern to show our concept is right. So we have to, I ask my graduate student to investigate the covering effect, the Marconi effect, the reusability. All of the motivation is to achieve nanoscale resolution by a general, very simple printing method. When we have achieved the nanoscale resolution, we have more for higher resolution, how to achieve molecular resolution pattern. So we have tried many methods. At last, we proposed the bubble template printing method to achieve the assembly and the pattern for molecular materials. Thank you.
Thank you very much. All right, so if Professor San, you're done, I can jump in and ask one question. I'm going to go back to a question that Professor San asked at the beginning of his question, where he's talking about interfaces being based on, I think it was Nick, being based on van der Waal forces. But you use those forces to project droplets in different shapes to, they change shape. Have you looked at how temperature and composition can affect that behavior? For example, if I have ethanol in water, as the drop is coming down, ethanol is going to be evaporating. So that should exert some force on the droplet. So will the drop bounce differently if it has something else in it and the surface tension changes? Will the drop bounce differently if I change the temperature? And since you're using this for printing, how sensitive is that? Is 1 degree okay? Is 10 degree okay? Is 5 degree okay?
Yeah, you are right. Actually, the van der force is very important, yeah, especially for the interface. But we have a few investigation on this point about the temperature. It is very important during the evaporation process, and it is very critical for the assembly of nanoparticle. We have a few papers about 7 years ago. Yeah, we investigated the different temperature, the Marconi effect, and also the Caffeine effect. Yeah, they have different effect under different temperature. And we found that about 75 centigrade is the best temperature for assembly our particle system to achieve uniform assembly. The higher and the lower temperature will have a different problem, such as the Caffeine effect and other undesired pattern. So thank you.
Yeah, and actually, can you comment on the bouncing bubbles on that same question? How does temperature and composition affect the bubbles that, you know, when you pattern the surface, hydrophobic and hydrophilic, and the bubbles were jumping like rats and all these shapes?
Yeah, you mean the
bouncing droplets?
The movement of the bubble drive the droplet on a hot surface?
No, you know, when you made the patterns and
yeah,
you had drops, when the drop falls, it forms different shapes. And then it bounces off, right?
Yeah.
That bouncing off, how is it affected by temperature?
It's not bouncing. It just we use a sandwich structure. The template, the ink, and the substrate is a sandwich structure. So the bubble is among the substrates and the template. So that we use the template, the pillar of silicon, to limit the growth of the bubble, and we pin the bubble with the nanoscale space and the capture. We can control the capture of the bubble, so we can balance the pressure of a different bubble. So finally, it is each bubble will form the same morphology, and the pressure is balanced. So based on this operation, we can assemble the well of the bubble into a desired pattern. Thank you.
Okay. Any other questions from the panelists?
Okay, maybe I go another questions. Actually, Professor Song, you have a very good experience for the commercialization of industry, fabrication for your technology, push forward. Can you give some comments, because in the audience, a lot of scientists was going to, commercialize their product or the technology.
Yeah, actually, it is very hard work to transfer your research from laboratory to industrial applications, because it is much more complex. If for writing a paper, you just can select your best result and you show we can do it. But for commercial products, you should make the same result each time, and you have to achieve sell it at a very cheaper price. So it is a challenge from a different point, not only technical point, but also other commercial and other even different culture. So I encourage my student to make effort to transfer the research, but not every student can be significant in business. So,
totally
thank you.
agree with that. Yeah. But one more thing, yeah. So if you are a young scientist, a junior one, so are you encouraging them to, attach with the commercialization or not? Because now, in China, many tenure track, yeah, many young, scientists was in the tenure track, so they have a big kind of pressures for publication, research, also for commercialization. Yeah, ask for. So can you give some comments for this?
Yeah, for young scientists, I think it's better to focus on your research on fundamental research. And if you have a special character, it means you want to achieve different life. You want to make money, you want to make success in business, you can try. But most PhD students are unsuitable for enterprises. So far, just one my postdoctor just one succeed in public company last year. Yeah.
Wow.
Very nice. Yeah.
Congratulations.
Yeah.
Yeah. So
Thank
Nick, yeah, I know your company already, close to public, right? So can you give some comments about this as a superstar, in science? So how you handle all this?
Yeah, I think what Professor Song recommended is absolutely true. The business side and I'll say the lab scale approach are very different. So it takes a lot of courage and different I'll say thinking to handle the pathway from the lab to commercialization. So I'm very fortunate to have team members who are really experienced entrepreneurs and businessmen. So I think it is very important to find your partner if you really want to go after the commercialization and pushing the technology forward to product.
Mm-hmm.
Okay, thank you.
Yeah. And Aris, if I can chime in a little bit. I think on the topic of commercialization, maybe it falls on us, the factor member, to educate students a little bit more on looking at business not as I'm going to make money, but more as I'm making my work impactful.
Yeah.
Because we can write a lot of papers, we can file a lot of patents, but it's only when we make a product that ends up in the consumer space that work has truly had impact. So I always advise my students that one of the things that they can do is, if you truly believe your work is good and you can provide a solution in an industry, you should explore the commercial space. And then you will figure out very quickly whether you are fit or you're not a fit. And some of them, because they believe in the work so much, they move on. My first postdoc actually developed heat-free solder and low-temperature solder and successfully built it from nothing all the way to a product in the market. And that spurred a lot of my other students to be interested in startups. So I think we might want to think about encouraging, giving the appropriate warning about the challenges and the mindsets in the business world versus academia, but letting the students follow their work, their PhD thesis into that space if they want to.
Okay, super. I know, North Carolina, they are really kind of have famous in this,
Yes.
training students for that. So that's a great, experience. So here is a question was from the audience was Zana. So he asking about what happened if the surface has a higher temperature? Well, melted. Professor Song.
Yeah. It's a famous concept named London Frost effect. Yeah, we all know on a hot pot, yeah, we'll have a bubble film. The bubble film will prevent it from high temperature, and this phenomenon have been prolonged a few hundred years ago. But our work is based on our patent surface. So we patent on the hot pot, and the different pattern will drive the droplet on the pot, yeah, to different dometic behavior to for rotation. So design the different pattern that have a different rotation behavior, and we can make use of the energy, not so high temperature for drive droplet. We call it a generator. Yeah, it's a new concept for macro scale generator. Thank you.
Okay, super. Actually, I'm looking for your next talk for the printed chemistry.
Yes.
Thank you.
That will be more fun.
Yep.
Thank you.
Very good.
Done.
We are at 9:30 right now, so I in my place, so I want to move on, and I want to thank everyone for your participation. And with that, I want to present this certificate to Professor Song. Very, very inspiring talk. Very exciting. I'm in the same field, so I'm delighted to be giving you this certificate. Now, since we're in virtual space, this will be sent to you later, and we thank you for your talk. I also want to make, I also want to make a few announcements. I want to remind everyone that we have the iCANX Davos Summit coming up in the summer. Exciting time. Come join the world. The world is convening not for G7, but for science this time. It's going to be all about innovation, science, technology, and investment. Completing the circle in science, technology, whatever we do, and taking it all the way to the marketplace. So it's time to meet. It's time to complete the circle. And I wanted to remind all of you that next week we're going to be having one of our very own, Chris Nyhouse, hosting a group that is going to be talking about information processing in cognitive material. Super exciting talk, so please join us. And with that, I want to say thank you, everyone, and I will see you next week. Bye.
Thank you. See you.
Super. Hello, ladies and gentlemen, my dear friends. Welcome to iCANX Davos Summit. So this year we're going to have this big event in Davos, Switzerland. We have 6 topics: innovation, science, technology, investment, management, and entrepreneurship. Short for It's Time. So it's time for us to go together. It's time for us to all these inspiring talks for the future. We'll have a Nobel laureate firms. We'll have president of academic firms. We'll have president of university firms. All these big names will be here to talk about the future, what's going on for the future. We also invited all these world leaders, scientists, investment management to go together to talk about, what technology and science going to be for the future. And we're going to listen to many sharp talks. All these great figures was from each field. They will share the sharp ideas, the latest results. So it's not only a platform for all these big names, for these shining stars. We also invite you to share your stories. So it's time for you to deliver a talk here. So you are welcome to submit your materials online. So we have many sub-sessions. sessions, parallel sessions, you are welcome to submit your materials, and we're going to pick up someone to share that. And it's our time also invite you to be superstars on the stage. If you are college students, welcome to apply for Innovation Award. If you are young scientists, welcome to apply Young Scientist Award. If you already have your startup, welcome to our Startup Award. All these applications is due April 1st, so you have about months to submit it. And it's time for us to go together. We have all these people here who want to work together with you. So we from different continentals, different countries, different areas. So welcome to join us. And it's our time to go to Davos. Now the pre-registration is open now. You are welcome to submit online and go summit together.
OIS compensates for optical camera shake by suppressing vibrations along the three X, Y, and Z axes to provide powerful image stabilization. One familiar application of OIS is in smartphone cameras. Using a TDK gyroscope, accelerometer, and chamber sensor, the OIS algorithm can detect various types of camera shake and compensate by moving the lens using TDK actuators. OIS has many more applications beyond smartphones, from everyday devices like VR and AR goggles and cameras to precision robots and drones. OIS has become an important technology for various devices that require